Hi, welcome to the latest Wikibon Angles. I'm James Kubilis. I'm here with my colleague George Gilbert. And what we're going to be talking about today is a topic that we discussed yesterday, George and I. It's in the next generation, this new generation of applications that involve both traditional coding with the deterministic, business logic, as well as the new generation of more probabilistic application logic, machine learning, and so forth. The equivalence of maintenance, code maintenance versus model training. And George had some ideas, and George, I'd like for you to kick it off by discussing what you're talking about here in terms of this evolution or this equivalency of maintenance to training for developers. It's a developer's topic, obviously.
It's both for developers and really the end customer for an application.
Right. And of course, data scientists as sort of a subset of developers broadly interpreted. Go ahead.
So for the longest time, since the beginning of time, since Noah's Ark, all enterprise software had a maintenance release schedule. And typically, like in ERP, it was updates to tax law and HR regulations. And this injection of new functionality in point releases, point 1 or 0.01 releases, that kept the software up to functional legal requirements, typically. And that was called software maintenance. And typically you paid anywhere between 18 and 22% of list price per year.
Right. You kept the software fit for some purpose that it was designated for.
Yes, so that it was
functional enhancements and so forth, right?
So that it still fulfilled its regulatory requirements for accounting and for HR.
Or its
and
functional
other things.
requirements as determined by the business stakeholders. Gotcha.
Yeah. So there was some malleability in terms of keeping it up to date. Now, with machine learning, when the models are created or customized by the end customer, the process of maintaining them and keeping them up to date, whether functionally or for regulatory requirements, that falls partly on the customer, on the end customer, and there's this process called ongoing training, or some people call it retraining, where
some people call it feedback. I've heard various terms.
Data feedback.
I think we're talking about this. Yeah. Yes.
There's a variety of terms. So your software vendor might give you like a fully trained model for tracking cybersecurity intrusions, in your network, or fraud prevention. And all of these have patterns that are rapidly evolving. And some of those patterns will be fed by your model provider, who will update the patterns that this will identify as malefactors. And at the same time, you will have incidents that are specific to your environment. And those changes have to get incorporated into the model.
The model as built may not be exactly right to predict the phenomenon of interest, the dependent variable that you're looking at. For example, whether somebody is likely to defraud you under particular circumstances.
And then one way to think of this is that when you put the model in place, its fit is pretty good.
Yeah.
But if you don't maintain it,
as
it
built
drifts
for the initial
as
scenario,
built.
But not for your specific environment yet.
And
you
then
don't know for sure.
as operated, if you don't change it, it'll drift and become less fit for purpose.
Right.
So between a combination of model feedback or data feedback from the vendor, potentially, and the end customer, you keep it as a high fidelity model. Now, one way to think about this.
There's a function called, or a topic called model decay that data scientists for a long time are quite familiar with. The model might have been perfectly predictive when it was initially deployed, but 6 months later it might be useless. It might be no better than a coin flip.
Model decay or drift. But it ties into something all developers and administrators and end customers of enterprise apps have always been accustomed to, which is what we call bit rot, which is if you don't,
Good term. I love it.
you don't do anything with your application, there's a certain rate of decay where it too drifts from its, fit for purpose. And the difference is in machine learning, the models can, once you have the proper operationalization capabilities, you can much more easily keep those models fit for purpose than you could in the old on-prem enterprise software era, where you actually had to upgrade the entire application to maintain it. Here, you can more surgically insert, a model that knows how to look for new types of malware or malefactors in penetrating your network.
Or you could have an execution environment that can automatically iterate up to a new version of the model that might have tweaked the feature engineering or might have tweaked the algorithm and so forth to keep, and then test that model or train it against fresh data. And in an ongoing, one of the established practices in data science is champion and challenger modeling. That if the champion model, the one that's in line, becomes less predictive, the best challenger model might be automatically elevated to production status based on its current fitness, based on its training against the latest and greatest data. I hear what you're saying.
And right now, that sort of capability where you're working with an operational host app, that's still a little immature, and most of that is roll your own right now.
Right.
But your point is spot on in the sense that just raw data feedback isn't always enough. You might need contextual data, additional contextual data. Say in the case of cybersecurity, you might get better whitelisting, and blacklisting, and those might be data feeds you didn't have before. And in that case, it's not just improving the training data and testing the model against new data. You're actually changing the model to become more fit.
Make it a new feed of data, a different type of data. For example, maybe your cybersecurity model has been built on transactional data you keep in your data warehouse about customer transaction patterns, but if maybe you incorporate a fresh feed of a new source, maybe mobile application data coming from your customers, and then use that, feed that into SCORE, train your model to get a better sense for whether that additional data can help your model be more predictive of the likelihood of fraud under particular circumstances. So yeah, sometimes a fresh feed and used in an ongoing training program on the model might make all the difference in terms of the model's effectiveness. Maybe you don't need to change the model. Maybe you simply need a fresh feed of data to give you that confidence that the model as built is sufficient for the purpose intended. Yeah.
Okay, but now let's look at it from a orthogonal angle, which is for customers that have varying amounts of internal skills related to data science. There's a range of things they can do in terms of, what they build and what they buy from external sources, because it's not black or white. You don't choose a machine learning model that's trained by your application vendor or build it yourself. There's actually a whole spectrum. And
that might be a starter model, purely a starter model. The manufacturer might say, we don't warrant your actual usage of our model in your circumstance. You need yourself to train it in your own environment to have confidence that it will do what it's intended to do. Yeah, so there's legal issues there, obviously, and issues in terms of warranties and so forth, depending on the kind of product,
And there are customers should understand that there's actually many levels that go into the sourcing versus buying, and it's not a white or black, yes or no choice, because it's a matter of at what level do you build on the shoulders of giants in the community, and where do you add your value? And let me go through a bunch of, a range or a spectrum of capabilities where you say, below this line, I'm leveraging the community, and above this line, I'm leveraging, my capabilities and my data.
Well, I think you have a really good framework. Go and discuss that. I saw that the other day.
So, all right, so let's say at the very bottom, when you're, for someone who's going to program all the way at the metal, literally, where they're working with the GPU practically. An example would be, in this case, a deep learning framework like TensorFlow or Caffe or
Theano, yeah.
Theano, yeah. There's even several more.
MXNet and so forth and so on.
So here, the people who can build that are world-class PhDs and engineers, world-class academics, really, and
or they might be right here in the Silicon Valley. Quite many of them
but they're
are, for example.
world-class.
Yeah, they're training it with perhaps simulated data they're doing it in the lab.
But
for
actually, I'm not actually even at the training level yet. I'm just talking about building this raw, generalized framework that people would build deep learning models on.
Oh yes,
because this is like a development framework and a runtime engine, all together. So and it knows how to scale out. It knows how to take advantage of advanced specialized chips that accelerate this sort of capability. But the key is, as we go up the abstraction layers, it is more democratized and accessible to a bigger audience. So down at this level, there's the rocket scientists at Google, who know how to build this stuff, the Google Brain team. But, like Evel Knievel, jumping the Snake River Canyon, don't try this at home. Now, the people who can build on that are typically PhDs and ISV developers who also extremely well trained, but maybe not the leading lights of the industry. Then there are the more familiar algorithms like the statistical ones, whether it's linear regression, logistic regression, the classifiers, things like that. Those two are created by PhDs, maybe not necessarily the world-class ones that are being poached for, 10 to 100 million per head. But with those algorithms in place, data scientists can then use them and put their training data in, modify the knobs that indicate what data is more important relative to other things.
Right.
Something called feature selection and engineering, and then one level higher, you might have a model built on that one of those algorithms that's a template, let's say, for credit card fraud prevention. Here you would have subject matter experts working with the data scientists to say, now what are the factors we should be looking for, and what are the data feeds we need to accurately predict what's a fraudulent transaction in a small amount of time without annoying customers by cutting off too many legitimate transactions. And that's ISV and corporate developers. Now, I don't know that we want to go, all the way through every level, but the idea is, at the highest level, you might have a predictive model that's fully packaged up. Let's say something like, let's imagine that Microsoft is leveraging all the amazing data they have in their Bing web crawls and their knowledge graph and all the speech to text that they've taken in from their phone apps, so they have natural language understanding. So these are rich and fully trained deep learning models, and they get smarter over time because Microsoft's also collecting more of this data and learning from it continually. So that would be at the highest level. So there, if you wanted to build a interactive voice response call center capability, that with Microsoft's technology, you're going to get world-class voice recognition or speech recognition. You're going to get world-class mapping of the customer intent into a sentence that you can parse. And so when you look at the spectrum of all these capabilities, you have to determine what skills you see yourself capable of acquiring and retaining in-house. And you also see which capabilities you need to be differentiate it on, because you might not take just the raw Microsoft conversational user interface. You might put a model in front of it that specializes it for outdoor camping equipment.
Right.
You know, so it understands those capabilities that might not have been in the Microsoft one. So you've got a kind of a compound model.
Or you might even retrain the model. Let's say it was trained, let's say there's a natural language process interface. It was trained for American English speakers, but you want to deploy the solution out to Singapore or India, where they speak English, but like if you're doing speech recognition using deep learning, you have to retrain it for the actual dialect and the accents of the people where in the target market. That might be an example. But also, you might need to retrain it. Like for example, autonomous vehicles are a huge R&D focus everywhere. You know, in the lab, you have these alpha versions of these autonomous vehicles that in many cases are been trained to simulate on simulated data that was built in the lab. Then you go out and retrain the prototypes in a physical proving ground. Like I know there's one. I grew up near Ann Arbor, Michigan. There's one out there. But ultimately, the deployed autonomous vehicles in the real world have to get retrained, as it were, on the fly from actual operational real-world geospatial streaming sensor data coming in from the actual vehicles and from vehicle-to-vehicle environments. So there's various levels of training that need to happen on the deployed models, whether you're talking about autonomous vehicles or any other product, over the life cycle of the things that these models
to keep it
power, to keep it fit, to make sure that it's fit for the intended purpose. In the lab, as to gin up an alpha of a product, the fitness needs to be the product performs according to some set of test procedures that are purely like bench testing. But in the real world, the fitness might be it doesn't crash cars and kill people, whatever, and under normal operating or even abnormal operating procedures. So you have to consider the whole notion of fitness changes throughout the life cycle of whatever it is you're building. Whether it's an autonomous vehicle or a chat bot or anything else that's powered by AI or machine learning, the whole notion of fitness needs to be evaluated. And what are the optimal training data that you need at each point to ensure? Go ahead.
You made an interesting point about how the initial training might happen in a lab. One of the things that's becoming more pervasive in machine learning is where you basically synthesize the initial training data. Like in
George,
many
we
cases,
need to wrap up. I'll give you 30 seconds, and then we need to wrap up this bit.
In many cases, in fact, many of the autonomous cars are using video games to simulate road conditions.
Yeah.
And then that sort of gives them the jump start they need to be able to go out in the physical environment. But the point is that we're going to get more and more creative about how we train these models.
Right. Yeah, simulators are really incredibly important in the development of these applications now in terms of the initial modeling and training. Hey, George, this has been great. I know we're going to keep these discussions going. This has been the latest installment of Wikibon Angles. I'm James Kabilas. I'm speaking with my colleague, George Gilbert. If you want to get a deeper feed of the topics, the themes that we're stressing in our research here at Wikibon, we invite you to visit wikibon.com. And want to thank you all for your day. And here we are from the beautiful glass-enclosed nerve center of theCUBE in Palo Alto, California, wishing you a good one.